the content will largely based on the work I've done with my PhD students, and also some other collaborators across the globe, especially guys from University of Oxford, Felix and David. I guess most of you actually know them. So just about the strange name we have about the group we call the GLAPS. So it's the group of machine learning, numerical algorithm, computer vision, healthcare, and plus X. So I have to say, I'm, computation imaging is probably my second major. I'm still a student here, so I'm learning this field, and I'm very happy to be here and learning a lot of physical problems. That's what I'm interested in. So what my group is doing nowadays is basically we do everything around deep learning. I'm teaching deep learning. I'm doing research around deep learning. I'm using deep learning to solve all kinds of problems nowadays. So just to give you some idea about what we're doing in my group, one direction is that we're interested in to make deep learning trustworthy, especially problems like robustness, fairness, interpretability. And the second direction is about the computation for deep learning. So if you watch out, when we apply deep learning to a lot of physical science problems, we often face some constraints. But the current deep learning framework actually, they can't handle constraints like PyTorch or TensorFlow. If you want to handle constraints, you probably turn constraints into penalty function. But that means you probably can find some infeasible solution or a physical solution. So actually, recently we built some software package that can directly handle constrained deep learning problem of this kind, where especially in the constraint function, you can have neural network. And the third direction, which is actually occupying my group quite a bit, we have 5 or 6 active projects with medical school. We do all kind of medical image analysis, where we try to extract useful information from medical images of all modalities. And then we provide useful information to doctors. And the last direction, which is the thing I'm going to talk about today, is basically deep learning for science or engineering. Basically, our interest is to see how much deep learning revolution can actually change science overall. Especially, we're interested in using deep learning to solve some very hard scientific problem. Phase retrieval is one of them, I believe. Okay, so again, my background is mostly from computer vision or signal processing background. I'm not a computation imaging expert. So actually, when I communicate with these folks, machine learning guys or signal processing guys, when you say phase retrieval, in their mind, by the way, so actually that will be the next slide. So I learned all these things from actually, wait a moment. From a workshop that happened in IMA, University of Minnesota, that's 5 years ago. So there was a similar workshop of this nature where the idea was to bring together applied mathematicians, signal processing guys, and imaging experts to talk to each other and learn from each other. And that was quite successful. And I think I especially want to highlight the picture there, and I think all of us should remember this guy, right? Do you guys see what this guy is? Fine up. Yes. Unfortunately, he's not here this time, but anyway, so when you talk to machine learning guys or signal processing guys, when you say phase retrieval, actually in their mind, they are thinking about this one. They're thinking about the canonical phase retrieval where you do have the oversampled Fourier magnitudes and you want to recover the phase. But these different settings of phase retrieval are probably out of their dictionary. At least for me, initially, I only know the canonical version. And then over years, I try to learn all others, from workshop or from colleagues, from collaborators. Why I want to bring this up? Because actually, we talk about phase retrieval all the time throughout the workshop. And one thing I think we can overlook is that actually these phase retrieval problems have different level of difficulties. Okay, that's probably one thing that we overlooked. What do I mean by that? Well, let's do a simple test, actually. My simple test is that if your phase retrieval problem can be solved by least square, then I think it's an easy problem. If you can't solve it using least square, it's a hard problem. It's a hardware phase retrieval. So I'll just take 3 examples. Gaussian phase retrieval, of course, I know a lot of you wouldn't think this is a realistic phase retrieval problem, but at least this is popular in applied math community for a while. First node phase retrieval, the near field variant, right? And also the canonical variant, the far field variant. By the way, this is very awkward. So if we carefully think about these problems, they have different level of symmetries, right? The first 2, we only have the global phase symmetry, but the last one actually have 3 group of symmetries. And that practically actually map to the difficulty levels of the problems. Actually, I want to produce some plot here, but unfortunately we run out of time when preparing the slides. But I believe you observe in practice, actually the first 2, if you solve a least square formulation of this problem, you can easily solve them. Although, yes, I know you may complain about speed, right? The speed may not be great, but if you are patient enough, you'll find a solution. But this last one, if you run like 100 random initialization, 1,000 random initialization, probably you always get stuck at a local minima. You get something that, sometimes a superposition of solutions, sometimes just like random noise. So my point here is that actually, there's a whole spectrum of difficulty levels when we really work on phase retrieval problems. And we probably need to make it clear to especially outsiders, like machine learning guys or signal processing guys, which version we are solving. So the focus of this talk is going to be the hardest variant. In my mind, that's the hardest variant. That's the canonical variant. And I want to remind you of these familiar symmetries. We have 3 group symmetries, and really the second one, the third one, I think actually caused the essential difficulty of the problem. I think the flating and shift really caused the essential difficulty problem. The reason is that that's not very compatible with the space we're working with, right? Because if you think about translating the image content in the image space, that may distort the space quite a bit, right? So you cause some very strange landscape when you do optimization. So, of course, the thing I'm going to talk about is deep learning, how deep learning actually will approach these problems. I want to take a step back and talk about the general flavor of how deep learning solves inverse problems in general nowadays. So we are probably familiar with inverse problems. I just want to take quick examples from the field I'm familiar with, from computer vision, image denoising, image super resolution, computer vision itself as a big pipeline where we want to reconstruct 3D objects from multiple images. And also a lot of scientific and medical applications, of course. We talk about all the physical problems are inverse problems, of course. So traditionally, we would formulate inverse problem as a regularized data fitting problem, where you have a data fitting term, and then you have a regularization term that's trying to encode all kind of information you have about the object. Now, of course, there's a lot of limitations about the traditional method. Well, probably you complain about speed, but actually some very practical question is that which L and which R to choose, right? So the L normally would try to model the noise model, but the thing is that for a lot of applications, you actually don't have a good noise model. Or maybe you know the noise model, but you don't know which L to choose. The mathematical formulation, sometimes very powerless when you try to describe things. Similarly for R, you may obviously see some pattern there, but you don't know how to describe in math. Of course, in past decades, we are all, being educated by sparsity, right? We can encode the sparsity we know, which is quite universal to some extent. But there are still a lot of other patterns where obviously our eyes can see, but you can't encode in math, right? So deep learning actually brings in a lot of opportunities in, tackling these limitations. I would roughly group deep learning method for inverse problem into 3 groups. The first group, I call it a radical way, where we have seen a lot throughout the workshop, where the radical way is basically we try to collect a large training set, right? X and Y pairs. And basically we try to use neural network to approximate the inverse map. Which sounds like very naive, very straightforward, but actually there's a lot of practical questions. Of course, you always ask, whether we can collect enough data, which can be challenging for a new problem, for example. If you are trying to image something that's totally new, you have never seen before, black hole, for example, right? There's no way you can collect realistic data, right? And also, we complain that you are not using the physical model itself, right? Why want to discard the physical model if we have a good physical model? But actually, there's something more tricky there. Actually, this is an aspect I don't agree with our previous speaker. He said, the degradation in the quality is due to the network size. But actually, I think that's more secondary reason. The primary reason is that there's actually a very tricky learning problem because of the symmetries. So let me explain what happens here. So let's actually think about a simple learning problem where we try to learn to take square root. Okay. So let's say our data point x, we have a lot of x taken from the real line, and then the y-i's corresponding to squares. Now we throw in a y, and then we hope to get x, right? Now, imagine we get many, many data points here. And what can happen here is that you may see cases where your input y are very close, but actually the corresponding x have different signs, right? So if you have that kind of situation, that means the function you try to approximate is something like this. Okay, so this one you can imagine I take a lot of training points, and this is a function I try to approximate using neural network. And this is a dauntingly hard learning problem. Because although deep learning, neural network, in theory can approximate arbitrary reasonable functions, which is called a universal approximation theorem, right? But it actually struggles a lot when you try to learn functions that are highly arbitrary, something like this. So actually, if you implement this one-dimensional learning problem, you learn this. No matter how hard you tune the parameters or network structures, you learn this. Basically, it's something trivial. It's like neural network just give up. And also, there's something that's very ironic here is that actually the problem is harder when you can collect more data points, right? Because when you collect more data points, they become denser and denser, and this function effectively behaves like a discontinuous function, if you think about it. And neural network is not good at learning these kind of functions. Now, of course, you may say, okay, this simple one, I have a clever solution. Well, why not just fix all the signs, right? I can easily fix all the signs to positive. And then the problem is gone, right? And I pre-process my data, right? My data set. Now the function I'm trying to approximate is only in the upper branch. And now you train a neural network, yes, you get something nice. But actually, for practical problems with a lot of symmetries like phase retrieval, this is non-trivial, highly non-trivial, I can tell you. Just to remind you, we have 3 symmetries in phase retrieval. And it turns out that it is possible to break the global phase and flipping symmetry well, mathematically rigorous. But it's actually hard to break the centering, break the shift symmetry. So actually, we have done some work there in this workshop paper where we break the other 2 symmetry rigorously, but for the shift symmetry, we don't have good ways. We don't have any mathematical rigorous ways. We can only center the objects. But it turns out the learning becomes much more efficient after you've done this. Okay, so the point I want to make here is that actually for nonlinear inverse problem in general, and the phase retrieval in particular, I think all phase retrieval problems we face have symmetries, right? Obviously. You have to think carefully about this. And actually you suffer more as you collect more data. That's the takeaway message, and you have to carefully think about how do you pre-process the data if you want to do efficient learning. And then there's a second family of deep learning approach, right, which I call the middle way. The middle way is saying, let's bring back the physical model F, right? So let's, instead of throw away all our traditional wisdom, let's actually try to build on top of that. So the overall flavor is that let's try to revamp our numerical method for solving this kind of regularized data fitting process by plugging in some deep learning components. That's the overall flavor. Just to give you some samples here, one family called algorithm unrolling, which is based on the idea that any iterative method is basically a nonlinear, iterative nonlinear mapping that's mapping from the previous entries to the next entries, right? Then why not making the mapping learnable, right, if that's the case? So that's basically the idea. Of course, this is still data-driven, by the way. You learn that mapping by, massive amount of data. And the second family called plug and play. Here is the case where, if you are, say, doing image deblurring or image denoising, let's say, and you hope to find some R actually help you to denoise the image, then the idea is that why not just directly, we have some proximal operation here. Why not just directly take in some existing denoiser there instead of doing something mathematical, right? So that's called a plug and play. And then there's another family idea called deep generative models. So this family idea is actually especially applicable to natural images, where it's saying, natural images we believe they are not dense in the space, right? They form some kind of surfaces, or if you like, manifolds in the image space. So let's try to learn the data manifold first through this, where G is a neural network. And then when you try to solve a new instance, let me try to parameterize my data points as lying on this manifold. Okay, so this is another family idea. So I'm not complete here, of course. There are good surveys about all these methods. I would highly recommend this paper, this survey paper. Although I have to say the limitation of this survey paper is that it only focuses on linear inverse problems, where a lot of difficulty about nonlinear problems are not revealed here. And also, you may have some complaints about the middle way also, it depends on data, depend on the algorithm you choose. If you want to do algorithm unrolling, it's not every algorithm will work. And also, actually, if you look around papers around for phase retrieval, you'll see that actually before they do the unrolling or whatever, they actually need HIO to do initialization. That means actually the essential difficulty is still there. It's not that the deep learning magically solved the difficult problem. It's just that I would say it's more like deep learning do some refinement on your initial solution. And I'm going to focus on the third approach, which I will call the deep image prior. Actually, a lot of people have talked about this one. So this one actually looks superficially similar to the generative models, the deep generative models. Right here, we parameterize our object as the output of the neural network. And after this, you can replace your object just by this reparameterization. Okay. But one thing I want to emphasize here is that this is actually very, very different from the deep generative models. Because deep generative models, they still have a training set. And they would train this G theta beforehand, and then they plug in. And then their optimization is with respect to the seed Z. The deep image prior is no training data approach. There's zero training data. What you do is basically you just parameterize or reparameterize your X as this. That's it. So I would largely classify it still as the classic method instead of the data-driven method. And actually, if you look around, there are a huge amount of successes among DIP. The original paper actually do image denoising, imprinting, and other basic image processing stuff. And then later people extend this to deblurring, deconvolution, and other domains, MI reconstruction. And this thing is right now very popular in 3D vision, in 3D computer vision, where people try to reconstruct 3D objects. And also phase retrieval, this is something my group is doing. And many others, even beyond images. People have applied this to audio data, to time series data, and others. Now, I want to quickly mention actually a variant of this. This is called, in computer vision, this is called a neural implicit representation. So the DIP approach is parameterize the object as the output of the neural network. This approach is thinking of the object directly as a neural network. Because, for example, if we have an image, we can think that as a continuous function on R2, right? After that, you take a discretized operator and discretize that into a matrix. And actually, if you talk to applied mathematicians, they use a different name, we call it PIN. They are basically the same idea. As I mentioned, right now, these two kind of variants are super popular in computer vision. Actually, this year, the CPR conference, they got 5 or 6 oral papers using this to do 3D reconstruction. This is one of the oral papers. I take this from one of the oral papers. Basically, they represent the whole radiation field using a continuous function, which is parameterized by a neural network. Now, I want to zoom into our phase retrieval problem. And I just want to remind you, if you directly solve the least square problem, it won't work for phase retrieval. Just to set the ground a little bit, in case you're not familiar with HIO, the way to think about HIO is that instead of solving the problem in the original space, so here X is still in the original n by n space, and your measurement is in m by m space, okay? Instead of doing that, we would over-parameterize X as m by m. That means it's the same size as the measurement. Now, after you over-parameterize, you have two sets of constraints. One is the measurement itself, and the other one is that when you over-parameterize, there's some part of that off the support that should be 0, so you have some support constraint. And you have two group constraints, and then you can apply a method from numerical operation that's called alternating projection, right? And actually, up to date, I think most of the numerical method, or most successful numerical method for classic phase retrieval, they are variants of the generalized alternating projection. They're not a canonical variant, by the way. The canonical variant is the error reduction, but that doesn't work well, right, if you directly apply that. So all these are variants of that. This is the HIO method itself. I believe most of you are probably familiar with this. And one thing I want to point out, this is actually not very, at least from machine learning and signal processing, a lot of them don't know this when they work on phase retrieval, is that actually the hard part is about the initial support. If you look at papers that people have published, they use natural image to do the test. And natural image, we don't have any translation freedom there. So that makes the problem easier, right? Because you kill one symmetry there. So the actual difficulty comes from this initial loose support specification. And if you have this, then if you directly run HIO, it doesn't work. Then you need to use this fancy and wonderful trick. Is it by you, Stephanie? Invented by you, right? Okay. Called shrink wrap. So it's very necessary you apply this to make it work in practice. And just we want to give you a flavor of the whole pipeline. We can take this from the Oxford group, physics group. So this is a practical algorithm they use. When they try to work on the BCDI data, what they do is that they have multiple cycles of HIO plus ER. And you need to carefully choose these parameters in order to get them work well. And actually, you can see the periodicity of the cycles. Actually, each of them corresponding one, some HIO step plus some ER step. And my point here is that actually, you think about the algorithm, how many parameters we need to choose? Well, HIO itself has a parameter, right? And then you need to do shrink wrap. There are at least 2 parameters, sometimes 3. And then you need to choose these parameters, right? I guess it's roughly another 3 parameters. So in total, we have 6 parameters in order to get this work in practice. So now how do we tell that works or not? Well, I don't know. That's probably us, So if I have to complain about this, then I will complain about the hyperparameter tuning. That's painful, I think, overall. And also, it's sensitive to the initial support. Is sometimes even we do hard tuning, we won't get a very good quality. I'm going to show you some example later. And also, there are some local issues for some imaging modalities. Sometimes you have to do beam stop. That means you miss some data, and sometimes you have to deal with significant short noise. Now, let's back to our least square formulation, which actually fails if you just do it naively. Now, actually, let's bring back our DIP idea. So now what happens if I plug in DIP? Does that work? I just do this. This is simple enough, right? I just plug in DIP to this least square formulation. Does that work? Well, actually, it works to some extent. You observe, you actually recover the support quite well. Look at this support recovery. But actually, the complex phases, they are a bit off. Okay, so this is not too bad, right? I mean, if you want to do some refinement, you can take the support and then continue to do some refinement, because the support estimation is the hard part. But actually, we don't need to do that. Actually, it turns out that if we carefully reparameterize the object, we can actually get it work without other methods. What we do is that we can use two DIPs. Remember, we're dealing with complex objects, so we can naturally have magnitude and phase. So we can parameterize the object as actually the magnitude part, which is one dp per hour, and then the complex phase part, which is another dp per hour. This is especially appropriate for example, BCDI application, where we know the crystal, the magnitudes are either 0 or some constant, right? The magnitudes are uniform. And the complex phases can be much more complicated. So the asymmetry between the two objects kind of indicator is probably better to separate them when you do the reparameterization. Actually, when you work on some of the biological sensing problems, you need to separate the real and imaginary part based on the information available to you. I won't delve into this, but I want to emphasize this point, is that actually by using double DIP, we are just doing the information theoretical specification. That means we just specify the initial size as half of the measurement size in each direction. And also, we don't have any shrink wrap. Okay, we just directly do this. And this is the result we get on some simulated crystal data. You can check out these. Some of them are relatively simple. Some of them are complicated, especially in terms of the complex phases. So if you compare the result from HIO plus ER plus shrink wrap versus our method, you can see that, of course, magnitude, I think the support recovery, they are all doing fine. But if you look at the complex phases, I think this new method is doing much better, right? And also, we have some data on realistic 3D crystal measurements. And this one I think is interesting. So this one, John, is this one tuned by David? Oh yeah, so this one is interesting. So the Oxford group actually tried to optimize this one. We try to optimize that one. So actually independently compete with each other and try to optimize the result, and this is the comparison we get, okay? And I have to say there's a lot of limitations, of course, about DIP. Actually, some of the previous talks already mentioned about that. The most headache, the number one headache is that there's a strange phenomenon where when your measurement is noisy, you see you have this kind of bell-shaped curve. That means you get something very good to some point, and then it starts to degrade. Actually, there's some explanation for this, and this is quite universal when you apply DIP. When you do, for example, MRI reconstruction, you observe similar thing. And also, you can complain about the speed also, because intrinsically, this is also an iterative method. And also, which model to choose. This is kind of art, as I said. If you deal with the BCDI data, you probably want two DIPs. But in any case, I'm going to skip this slide. So we actually have a very simple early stopping method that's based on the running variance of the intermediate estimates. So basically, we keep track of them, and then if we plot the curve, you'll notice that the first value of the running variance actually is almost perfectly aligned with the best quality. So what we do is that we basically just keep track of this, and whenever we detect the first value, we just stop there. And another complaint about the speed. Recently, we actually figured out a way to actually substantially speed up, at least for preliminary test on image denoising, we can speed up by 20 times. We haven't got the result of phase retrieval yet, right? But okay. So this actually involves some modification to DIP itself. Actually, we switch the role of optimization. Instead of optimizing the network, we actually optimize the seed. The network now is totally random. And I want to highlight another application. Of course, this is out of interest of phase retrieval, but we actually used a similar idea, deep image prior, to solve this blind deconvolution problem, where the difficulty is that in solving blind deconvolution, normally we don't know the size of the kernel, okay? So this is the typical blur kernel. This is the clean image you are interested in. So normally, if I give you a blurry image, you don't know the size of the kernel. So traditional methods normally depend on the exact specification of the size. And as I said, this is used in image deblurring, and also in microscopic analysis, you can also model the motive detection as a deconvolution problem. And our recent work using similar idea, double DIP, we actually managed to overcome this substantial challenge about unknown kernel size. We're actually very aggressive in over-specifying the kernel size. We actually specify the kernel size of half of the image size. And it works. So another thing I want to bring up is about this data set thing. Because I work in computer vision for more than 10 years. So I understand the value of having some good and standardized data set there for motivating people to join the domain and join the effort. So if I look around phase retrieval community, I think this is something that's to some extent lacking. Yes, I talked to some of you, and there are enough data there, but I think it's just that we haven't put data in a well-organized way, well-documented way, so that machine learning hobbyists or machine learning students can either play with them and maybe just take them as a course project or something to start with, right? But so we are trying to do that. We actually generate a large-scale crystal-based data set, and roughly have 100 case samples, and also we have varying level of difficulty levels, different shapes, different number defects and densities. And we are going to release this in the coming months. Another thing I want to quickly talk about, this is also a little bit off the topic, is that so we probably haven't met the problem, yes. When we apply deep learning to these inverse problems, actually often we will face physical constraints. And as I mentioned at the start, actually the current deep learning framework can handle that. And we actually built this software package where we can directly handle nonlinear constraints, especially if this involves neural network. So we build this on top of PyTorch. That means you have auto differentiation, you have GPU support, you have tensor variable support, basically everything. So what you need to do is basically specify the function, and that's it. So just a couple of quick examples. You translate your mathematical problem into these lines, and then press the button and wait for something good. All right, so that's my last slides. We have several papers in the pipeline. Unfortunately, all of them are forthcoming. I hope to wrap them up soon and put on archive. And also, we have other related papers on DIP. And that's all I want to tell. Thanks.